The purpose of this presentation is to clarify the security model based on capabilities. We'll start with a brief explanation of the rationale for the model. We'll then illustrate the model through two examples. Today, when Notepad starts, it gets implicit authority, actually all the user's authority. This violates the principle of least authority. It makes running any application that is not 100% secure a huge risk. Constantly giving out excessive authority pretty much guarantees that that authority will get abused by compromised or malicious app. How can we rewrite our systems with better respect for the principle of least authority? First, Notepad should start with no authority by default. The question then becomes, how does Notepad get some authority? The authority actually needs to do some work. The answer is to combine the authority to operate on an object with the designation of that object. We'll first look at how this works at the object level, and then see how the same approach applies in the user interface. Let's consider two objects A and B. A has a reference to B. This gives A access to B, which means A can call B's methods. This type of reference, where you're granting access by simply pointing to an object, is called a capability reference. Let's add object C to the picture. C knows about A, but this doesn't mean that C knows about B, because A keeps its knowledge about B private. It's impossible for C to just invent a capability reference to B. Here's one way to think of this scenario. Imagine B is a resource that needs to be protected. A is a resource manager that encapsulates and guards access to B. C would be the application trying to gain access to resource B. A can either expose part of B's functionality indirectly, or it can decide to share its capability reference to B. For example, if C needed direct access to B, it would ask A to grant that access. If A accepts, it returns a capability reference to B, thus introducing B to C, and C now has direct access to B. This simple scenario may seem trivial, but it illustrates the mechanics of capability-based security. Resources like B are only accessible through capability references. This puts a burden on A to be responsible about the authority it holds, in addition to A's traditional functional responsibility as an object. This is why we call this approach authority-driven design. The access control is built into the design, rather than in an external entity, like in the case of ACLs. Let's now consider a higher-level scenario, looking at Bill's desktop. Bill is mostly a user of Notepad. He has a Notepad launcher on his desktop. He also has an icon for his personal file manager, an object that holds capability references to Bill's files and directories. Although the user doesn't see it, the Notepad launcher has a capability reference to the file manager. In this presentation, I won't go into the details of how the launcher got set up on the desktop, or how it got the capability reference to the file manager. Assume that this process is similar to today's installation experience. Double-clicking on the Notepad launcher spawns an instance of Notepad. That new process starts with only the authority that the launcher granted it. In this case, Notepad starts with a capability reference to the file manager. Bill then wants to look at a file and selects the Open menu in Notepad. Because Notepad itself doesn't know about any file, it needs to ask the file manager for a file capability reference that it can read from. It does so by calling the askForFile method exposed by the file manager. The file manager is programmed so that it doesn't simply give out authority for the files that it holds. Instead, it requires the user to give explicit approval. In our scenario, when Bill selects a file A from the chooser, he is giving approval to the file manager to share that file with Notepad. Here, Bill selects file A and clicks Grant Read Access. The file manager is now ready to complete the call from Notepad. Because Notepad only asks for a file to read, the file manager creates a read-only wrapper object for file A. That wrapper is then returned to Notepad. Notepad can now perform the read operations that it needs on the wrapper. That read-only wrapper only implements read methods, delegating the actual logic to the file A object. Enhancing the access control is just like adding any other feature. This example actually demonstrates a simple design that allows for safe read-only files. Other security features, like revocation or auditing, can also be built in using more elaborate patterns based on the same basic mechanics, while still keeping a very familiar user interface. Let's now consider how this model handles the threat that Notepad isn't actually a trustworthy program, maybe because it was downloaded off the web, or because it was corrupted by a virus. Let's say there was a vulnerability in Notepad and a hacker decides to exploit it to gain write access to file A or file B. What options are available to the hacker? In this diagram, Notepad has capability references to the file manager and the read-only wrapper for file A, and nothing else. These nodes act as guardians of Bill's files by preventing direct access. The hacker would have to compromise the nodes in order to get to either of these files. Because the authority is embedded in the design, it's not enough to compromise an application that has permissions. You need to work your way through to compromise the objects that hold the capability references that you target. Also, in the case of a more complex application that would need many different kinds of capabilities, you would break down the application itself into objects. That makes a hacker's job even harder, because the exploit will compromise one object inside Notepad instead of Notepad as a whole. This illustrates a simple case of defense in depth with fractal approach to security, in contrast with the current approach based on perimeter security. Now suppose a hacker decides to use a vulnerability in Notepad to commit some other malicious attacks. For his first attempt, he wants to infect some of Bill's system files so he can change the behavior of Windows. Unfortunately for the hacker, Notepad doesn't hold capability references to any system files. The hacker is blocked. For the second attack, the hacker wants to take advantage of Notepad's read access to file A. He tries to get Notepad to send file A to his remote server on the internet. Once again, the hacker is fooled because Notepad doesn't hold capability references to objects that manage access to the internet. Capability references cannot be pulled out of thin air. The direct benefit of this is that the hacker cannot elevate his authority beyond the scope of the capability references. The side benefit is that security reviews and threat models need only focus on the network created by the references. Everything else is out of scope. In this presentation, we introduce the concept of capability references and the simple mechanics that they follow. We illustrated how they extend object-oriented design to integrate the notions of authority and access. Similarly to object design patterns, access control patterns also appear. These authority design patterns can be studied and reused. Because the principle of least authority is built in from the core, systems built with capability discipline truly implement security in depth and are thus virtually invulnerable to viruses. Thank you for your attention.